Okay, so I'm gonna review everything we did last time really quickly because it was a lot. So so we did every little step in the solution to the quantum simple harmonic oscillator. And the quantum simple harmonic oscillator is just like the classical one, except the solutions look and act different because it's a quantum particle. We still have the potential v of x, we're in 1D, is 1/2 k x squared. But honestly, because this comes from force constants, and forces, you don't really talk about them in quantum mechanics, you talk about potentials. So instead, we'll rephrase this as 1/2 m omega naught squared. So that's like the natural angular frequency of the potential, if you're thinking about maybe trapping atoms in a laser or something like that, or a magneto-optical trap. So this is just the natural way of rephrasing that for quantum mechanics. And because you guys have been through modern, you know what the solutions should look like. So what we want are wave functions. And we're going to end up with a quantum number on the wave function. And the lowest one looks like a Gaussian, because it is a Gaussian. And it extends into the classically forbidden region. So this would be phi naught. And then the next excited state, first excited state, would look like a Gaussian, would look like a Gaussian times x. And we actually solve that. And then the next one would look like a Gaussian times x squared minus something, and so on. And so each one of these will have its own energy as well. So that's just the physics review. Okay, how we approach this is all of the details that you guys didn't get in modern, which is probably even including writing down the differential equation. So this is the time-independent Schrodinger equation. This is a Laplacian in 1D, just two derivatives. I like a Laplacian in 1D. There's our potential. That's a square. Okay. And we're going to call that star. That is the thing we want to solve, the time-independent Schrodinger equation. So step one was just clean up units. So this should have the same style of solution no matter what the mass of the particle is or if h bar is 1. So we just put things in natural units. And the natural units, just to remind you guys, look like this. Psi's in my notes, and I thought it would be a fun challenge to try to draw with the whiteboard tablet thingy. It was. And this is chosen because the units of psi are 1. Okay, this is something that you don't really have to do in a diffie-Q textbook, but again, this is what physics will give you. And then you can always ask, like, well, if you make it unitless, what's going on with that 2 there? The 2 turns out to make life a little bit easier. So this is sort of like the energy constant, and you saw how that showed up. So we just defined these 2 unitless things, and then that turned star into this beauty. So this is a much nicer differential equation than this, of course, right? Okay, up to some tricks, this is essentially what we did. And again, if you're stuck on a desert island and you need to solve a differential equation that you've never seen before, what you should always do is try a trial function, right? So this is sort of oracle of differential equations that if you write down a function, you put it into the differential equation and it solves the differential equation, it is the solution. And it doesn't matter if a gypsy told you what trial function it was. If it works, it works. And essentially what the method of Frobenius is to try the most general type of solution you can. And if you think about, Taylor series or Maclaurin series, you're like, well, I can represent things with polynomials, so why don't we try a polynomial? So the other way of thinking about it is like, we don't want to find our solution necessarily. We'd like to find the power series of our solution. And maybe we only need a finite number of these terms because as k goes to infinity, the ak, it just so happens like get smaller and smaller. Okay, so this is the general ideas. Try, if you don't have a better idea, just try this as a power series trial function. Okay, we had 2 refinements on this, but this is the essential idea. Again, desert island, if you have to solve a differential equation, try a power series, put it in, and then maybe, you'll figure out easier ways of doing it over the next 100 years of solving it. So any questions about that? Okay, this is the part where we have, over 200 years of hindsight. And we did this first. So what is R? So sometimes the solutions blow up. So imagine if R was -2. For the k equals 0 term, I could have 1 over xi squared. And maybe I have a 1 over xi squared singularity or something like that. So the most general thing we can write would be not just a polynomial, but also has blow-ups like 1 over xi to the first, second, third power. So sometimes our solutions blow up. Our solutions, we already know what they look like. This is the hand-waving kind of argument about our solutions don't blow up, so R equals 0. We don't need any R equals -2 terms or something like that. So the second thing we realized is that as psi goes to infinity, we should go to 0. Okay, that's always a great thing to note. But specifically, we can actually do a little bit better than that. And again, if you didn't do 2b, you would still get a usable indicial equation. You just be like, wow, there are a lot of terms, instead of the finite number that we end up working with. So specifically, as this goes to infinity, the psi term here is going to be really big, and the k term is going to be really small. So in that case, star goes to psi double star equals psi double star psi squared psi. Yeah. Greek, you know what I mean? So as we get to infinity, the k term is negligible. We end up with something like this, and that gives us an asymptotic solution that phi of psi needs to approach e to the minus psi squared over 2. Technically, plus or minus both solve this, but plus obviously is not going to work because that's going to blow up. So really physically, we have just the minus branch, right? Okay, so you can verify that that with the plus or minus solves this, but again, we need to go to 0. So we need the negative psi squared over 2. Okay, so with that update we had, okay, what we'll really do, because we have a little bit of, again, hindsight on this, we'll try our trial function of ak psi k e minus psi squared over 2. And then honestly, just dump this thing into star. And I would need to take 2 derivatives of this thing and then multiply it by psi squared minus k times the thing itself. So any questions about that? So I'm going to skip that. That's just a lot of algebra and calculus. That's the bulk of what we did. Okay. So we did algebra. And we did calculus. And this is the part that you might run into again, because there is a potential indicial equation in your future, depending on what homework you do, is we have this insight about series. Is that if I have ax squared plus bx plus c equals 3x squared minus 2x plus pi, and this is true for every single x in the real line, then I actually already have the solution, not of one thing, but of three things. So we have a term by term solution. What must be true is that a needs to be equal to 3. What must be true is that b needs to be equal to minus 2. And what must be true is c needs to be equal to pi. So if we equate coefficients term by term, which is to say the psi squared terms and the psi k terms, each one individually needs to be equated. So inside of that differential equation, we do all the algebra, we do all the calculus, and then ... When we equate things term by term, all of the, notice how there are no psi's or x's anywhere. I'm just literally saying a equals 3, b equals minus 2, c equals pi. So what you're really fighting for when you do a power series solution is what's called the indicial equation, which is like, well, if this is true for all x, I get this term by term thing. So k, 2k, I think. Yeah, 2k plus 1 minus kappa. Maybe k and kappa wasn't the best idea. Okay, so this is what's called the indicial equation. And something really nice happens is that for this one, so what you guys might see in the future is one where we have a coefficient or a constant like kappa, but it's downstairs. So that doesn't tell us where we stop, that tells us where we start, so we don't blow up. In this case, at some point, the numerator is going to vanish. And the numerator is going to stay vanished. Okay, so this is how we would then do stuff, is that you just find a solution by picking k or kappa, and then keep writing down terms until you run out of terms and it's a finite series. So that's where we got to. And it turns out that in essence is, if you remember what kappa was when we defined things, kappa is, going back to physics for a second, kappa is 2e over h bar omega naught. So, you're not going to change h bar, you're not going to change 2. Omega naught you chose at the hardware store when you built your magneto-optical trap. So what you're really doing is you're finding the solution at some energy. And in fact, what you've discovered is that the energies themselves are quantized. So if you solve this, you get the fact that, oops, so this is the integer where the series truncates. You get some finite number of series terms, you get an energy associated with that, and then we have a way of making phi of psi. It's always got this part, this asymptotic part we picked off, and then there's the series part in there. Okay, so that is all the steps. These are somewhat generic. What you should be expected to do on your own is if somebody says like, hey man, there's you should use the method of Frobenius to solve this thingy, and it's got a singularity, so you got to use r equals 2. You should be able to go through these steps and replicate this argument and use the indicial equation. If somebody needs to clean up constants, they'll probably do that for you, because as you can see with this like 2 in there, sometimes there's a little bit of you know, kind of magic knowledge where if that wasn't a 2, you'd have a harder time, and the asymptotic behavior, that was a little bit inspired too. So that's where we got to. Would you guys like to go through the generation of another, what are now called Hermite polynomial, through the indicial equation? That'd be worthwhile since we got it up.
What else would we do otherwise?
Just the remainder of the discussion about this is just talk about the properties of the Hermite polynomials, which are the things that show up here. And they're going to have some properties that don't necessarily surprise you. And then start talking about Bessel functions. So that's the agenda for today.
Personally, I'm kind of into Bessel functions, but I don't know. I think either way.
Okay, so these are things, you generate them by recursion. They're called Hermite polynomials. Okay. And, you know, until you, I mean, honestly, if you finish an undergrad physics degree and somebody stops you on the street and you know that Hermite polynomials solve the quantum oscillator, you know that Legendre polynomials are for multiple expansions and associated Legendre polynomials are for spherical harmonics, you're in really good shape. So part of what the problems that ask you to, you know, work with the recursion formulas and Rodriguez's formula and stuff like that do is it just grinds that into your brain enough that you kind of remember what these things are in the first place. Okay, so these polynomials. So we normalize them probably so that they work with the harmonic oscillator, and wave functions need to be normalized, but now we'll just write them all out. But if you look in a math book, the Hermite polynomials have their own personal normalization. Okay, so the first thing we did was we set that max value of the integer equal to 0. And then what we discovered is that we pick 1, for instance, for A0, and then series truncates. We don't get an A2, we don't get an A4, it's all done. The next thing we did was we picked A1 to be something. And then turns out the series truncated after that term too. A1 exists, but A3 truncates. When we pick 1 as the max value. Okay. However, because this thing has, you know, we're talking about k equals 1, we have a psi there. And because reasons, there's a 2 there. Right? So you can choose A0 yourself, and by convention, it's chosen to be 2. Okay. So if you see where this is going, tell me what the form of H2 the second Hermite polynomial is. Or H3 for that matter. Go all the way up to H4. So H4 is the one that might not be obvious. So think about how that indicial equation worked and what should H2 kind of look like. You don't have to worry about the numbers themselves. How many terms should I have?
Maybe two. One for the psi squared and one for the psi.
Yep. And then 2 powers less than that. Remember the series jumps by powers of 2.
Oh, I see. So just
and so you get a constant. And then I'll just put constant there because it turns out the constant has a negative 2 value. So okay, what would H3 look like?
similar, but with a psi to the fourth and a psi squared.
Similar, they're evens and odds. So you've got
Okay.
H4. So leading power shows up there. So to the fourth squared and then 0. So this is third, first. Writing 1 is kind of gratuitous, but we'll do it anyway. And then 8, and then 12, and then 16, 48, and then 12. Okay, do you guys see a pattern there? Of course, this goes on to infinity. And this would correspond to the thing that I multiply the exponential by to get the fourth excited state of the quantum oscillator. So 1, 2, 4, 8, 16, 2, well, nothing, minus 2, minus 12, minus 48. Looks like there's a pattern there. There's absolutely a pattern there. So there is a recursion formula. And it is hn plus 1. We've got to raise it by a power and multiply it by 2. So you can see that. We raised it by a power, multiplied by psi, and then multiplied by 2 for each of these leading coefficients. And then the next term is a little bit less obvious. So 2n times hn minus 1. So this, in some sense, is the indicial equation kind of manifest. Okay, and now I'm going to try to trick you. Please give me an answer, even though you know this is going to be wrong because I'm saying I'm trying to trick you. We'll just say this. So what we'd like to have is these things be normalized. And this is where mathematicians kind of get on the physicists' nerves a little bit. So the Hermite polynomials themselves aren't normalized in this form. This form is optimized to just have like the recursion relation look really easy. But imagine that I came up with these coefficients like this. What do you suppose I should put here? So what would you like to be true if H and HK and HJ are equal versus HJ and HK not equal? Maybe 44th time you guys have been asked this question.
Love it if it was the Kronecker delta.
Yeah, it'd be pretty cool if this is true. Just immediately looking at these polynomials, why on earth, you can immediately see that this isn't true. there's kind of a physics reason or a, just remembering what we did reason, but there's a deeper reason why this is true, because we haven't talked too much about Sturm-Liouville yet. Well, polynomials always go to infinity or negative infinity. So if I have two polynomials and I integrate up over the entire real line, they're going to blow up. So what's actually true is this. We have our old friend, whoops, we have two of them. So you have our old friend, the asymptotic behavior, and then this is true. Okay, what this thing is called, the e to the minus psi squared, is called the weight. And I'll just say HP for Hermite polynomials. So you can take an inner product, the overlap in between two functions. We usually just take the overlap in between the two functions. Here, we're actually defining overlap of two functions to include this. So the definition of inner product, if you're thinking about, Hermite polynomials, is, okay, multiply them together, integrate over the real line, but don't forget the fact that you have this asymptotic behavior. So this is how these are normalized by tradition. They're written so that they have this really nice recursion relationship. You've got to do extra work, two types of extra work, to make, the thing that we would like to be true is that Hermite polynomials are orthonormal to be true. So this is true if we put in the weight and if we have Cj equal to pi to the negative 1/4 power over 2 to the k factorial. So u. So this is the normalization. Okay, what's nice about this, however, is that because we're making our quantum mechanical wave functions out of this, I don't know why I have some weird square there. I think I just got really used to writing squared. So integrating by deke psi. That this is true. So these are the wave functions themselves, psi j and psi k. Okay, so we have a recursion formula, we have a table, we have the idea of weighted orthogonality, and I'm going to write what's true about these things. Under the recursion formula, so you have a kind of table of all the true things about Hermite polynomials. Again, these things can be orthogonal, you just got to do some work. So what's true, another way of stating it is that they're orthogonal if you use the weight and you have a little constant in front. Okay, the last thing I'll say is this does have what's similar to the Rodriguez form for this is Z, I think. It's not a Z. Why Spanish people even have a Z in their language? Doesn't make any sense. So it also has the Rodriguez form, which if you remember from our discussion about Legendre polynomials, was how you make one from taking a successive bunch of derivatives. So you can make the nth Hermite polynomial by taking derivatives of exponentials. So maybe I'll ask you guys to do this once to try it out. I actually can't remember. I think this is the last thing on the problem set due today. Yeah, just doing this. So essentially you take a bunch of derivatives of the exponential and then you get rid of it with this thing out in front and then you correct the sign. So actually this Rodriguez form is pretty cool. It works, in my opinion, much better than the, or looks more elegant than the one for the Legendre polynomials. Okay, so there will be kind of a wrap up now that we've seen 3 of these. We're about to go into Bessel functions of all of this stuff kind of smells the same. Orthogonality, recursion, Rodriguez form for different, seemingly very different differential equations. And I've been hinting at the Sturm-Liouville stuff. There's a theorem that says if the differential equation can be put in this form, I can't tell you exactly what it is, but I can guarantee that all of this stuff will exist. So now that we have 3 examples, I can, we won't go through it in class unless you guys ask. I'll just record that and put it up. So there will be another one, and there will be Bessel functions, and that'll be our 3rd example of this whole kind of machinery. But any questions about Hermite polynomials before we move on?